All right, so I'm super excited. Today I want to talk about a topic that I'm extremely passionate about, fairness in machine learning. Many of you in the audience are machine learning practitioners, data scientists, and might be thinking about incorporating fairness into machine learning systems. So today I want to focus on some of the practical challenges that come when you try to operationalize fairness into machine learning systems and some methods to address them. Okay. All right, so this is joint work with my collaborators across Google and my PhD research institute, Max Planck Institute in Saarland University, where I did my PhD topic on this topic. Okay, so ML fairness is not new. It has been around for a while, and I think a lot of you have heard about it. This is a growing research community. It started off with a workshop at NeurIPS. Now it has its own conference. A number of books have been published on this topic, has led to a lot of calls for action across industry as well as academia, and Google itself also has its AI principles, and many of the other places in industry have that as well. So this is all great. Yet when you think about, so ML fairness has made tremendous progress, but there are yet many open problems and challenges when it comes to addressing them in practice. So the goal of my talk today is to shed light on some of these ML challenges in practice, present some approaches to handle them, and sort of also set a stage for the roundtable discussion that happens today later on this topic. Okay, so typically ML fairness in research looks something like this, at least back when I did my PhD on this topic. So you assume that there is already an existing academic data set with predefined protected attributes and features like race, gender, and so on. And then you define your fairness notion. Maybe if it is college admission, you could say that it is unfair to reject a qualified candidate, or false negatives are unfair. And then you can define a machine learning objective, maybe equalize false negative rates across various different groups. And then you sort of go ahead and evaluate this on a test set, which is already given, and all is good, and perhaps you publish a paper. This doesn't really look the same when you look at this in practice. And bias creeps in at a lot of different points in your machine learning pipeline in practice. And you can think of incorporating fairness at each of these different steps of the machine learning pipeline, right from problem formulation to model development, deployment, and all the way to continuous monitoring. So in my talk today, I'll focus on some of these challenges in a subset of this pipeline, mostly on model learning and the steps that happen thereafter. Okay, so let's get started with the first part of model learning. I spoke about fairness in machine learning, and one of the key challenges in practice that happens is you don't often know which group needs fairness intervention. What are the groups where your model might be biased against? And often you don't even have sensitive attributes in your data sets. So how do you even train a fair machine learning model when you don't know which groups need fairness, and you don't have access to the protected attributes? So in our NeurIPS paper, we tackled specifically this problem. So let me formulate this a little mathematically first. So given a data set, but no observed group memberships, that is, there is no attributes on race or gender, you want to learn a fair model which is fair towards all of these groups. So the notion of fairness over here, we formulate it as Rawlsian maximum fairness. So the goal is to maximize the minimum utility across any of these groups. We set this up as a mini-match problem. You can think of it as a two-player game between your main model that sort of wants to learn the best possible classifier for this, and then there is an adversary which sort of tries to identify the worst of group and puts all of its weight there in order to sort of learn an optimal algorithm in the end to minimize the losses for the worst of group. Now, if you knew group memberships, you could assign these weights in such a way that you find an optimal solution, right? But the problem is we don't know these groups, so we don't know what's the loss for these groups. So the key insight that we had here was in the absence of group membership, perhaps it's best to focus on the worst-case computable regions of high loss. So let me illustrate this with an example of what I mean by computable regions of high loss. So consider a toy example. This is a binary classification task. Dots and crosses are your two classes. Now, our data points come from two groups, but we don't know these groups. It's not observed in the data set. All you observe is the position on x-axis and y-axis. Now, observe that even though we don't have access to the groups, oftentimes group membership, for example here, orange group, is correlated with the position on y-axis. And these are the reasons, so this happens to be one of the correlation between observed groups and what you have in the data is often the cause for unfairness concerns, that you might be training a biased model. But you can, in the case of fairness without demographics, this is a key insight that you can actually use to train a better model. So a practical example is, for example, race is often correlated with the zip code. So even if you don't have race in your data set, your model might still be biased against people in this group. But how can we flip this around and actually use this to train a better model? So let's go back to the model that I was mentioning. Let's look at the same data now without access to the group membership. And this is a simple group agnostic classifier trained. The points in red are the errors made by the model. Observe that there is this region in the input space where the model is making systematical errors. That is, it's misclassifying a lot of points in this region, right? And these errors are different from your errors due to outliers, which are more uniformly or randomly distributed in the input space. So the idea here is that these systematic errors due to unfairness are likely to coincide with such computable regions of high loss in the input space. And focusing on such computable regions of errors can help mitigate systematic errors towards groups. So with that, we propose adversarially reweighted learning, where the idea is really to identify such computable regions of loss and alternatively train in a way such that you focus the model each time on such high regions of loss and hope to improve in that space. Okay, so I'll just present one slide on the results here. So we explored this on a number of academic data sets. Here, the protected features were, for example, race and gender. These are used only for evaluation. We don't really have access to them while we train the model. And what we observed was that across all of these different data sets, the proposed method that I had not only improves the AUC for the worst of groups, but it also improved the overall model because you were actually training a better model that works well across these spaces. Okay, so I think with that I go to the second part. So now say we have trained a fair machine learning model. Now you're trying to deploy it in practice, and another thing that comes up is often models are not applied, so your data distribution where you're applying might not be the same as the one you've trained it on or even tested it on. Often models are applied to underrepresented groups that might not be really there in your data. So the question is, can you trust a model's prediction? More formally, the question here that we had is, we already have a trained machine learning model. Can we estimate the uncertainties of this model, but in a black box manner? That is, we don't make any assumptions about this model, and we don't have access to the model itself or its loss functions, just the eventual classifier predictions. So in this work, we presented this risk advisor framework. So very high level. So the idea is you only have the access to the input data and the predictions of your black box model. And the goal is to train a risk estimator which can be applied post hoc to an already trained machine learning model. And the main insight of this work was that in the absence of access to a black box model, estimating the uncertainties of a meta task, which is trying to predict where the underlying model is going to make errors, is a very good proxy for estimating uncertainties of the black box model. I'm not going to talk into the detail about how we estimated these uncertainties or anything, but I'll give you some intuitive insight into how this can actually happen, that you can estimate uncertainties in a black box manner. So let's again consider a toy example, a classification task here. The black and the white data points are two different classes. Now the setup is where your test distribution differs from the training data, and a black box model here, an SVM applied to this, make three different varieties of failures here. So the first are errors due to model limitations. Your data is nonlinear. You've applied a linear SVM, let's say here. The points in the red are simply because you've chosen a bad model. Then there are errors due to noisy data. When the two classes are overlapping, this is the best that the model can do in this space. Then there are errors due to data shift between the training data and the test data. Now let's look at the same setup, but from the perspective of the meta-learner. Let's recall that the meta-learner has only access to the input data, so the same data that you see here, and it also has access to what were the training errors made by this model. Observe that these errors due to model limitations sort of appear as predictable errors in this space. And the errors where the underlying SVM had uncertainties due to data, like inherent noise or shift in the data space, the meta-learner also has uncertainty here because it cannot really predict whether there is whether the underlying model would make an error here or not. So we can use this insight to actually estimate the uncertainties of the underlying model. Some result on this. So we actually tested this by recreating these different failure modes that I mentioned earlier, errors due to inherent noise. For example, for this, we considered high-dimensional vision data sets like CFAR and Fashion MNIST to replicate the scenario of failure due to shifting regions. So we consider data sets like health, heart disease, where your training data is on the US population and you're applying the model on data points from other regions. Similarly, for fairness scenarios, we sort of applied this for example, census income task, where your training data only has male data points, but you're trying to predict it on underrepresented groups that were not even seen. And recall I mentioned that the risk advisor is model agnostic. So sort of we took these data sets and applied out-of-the-box machine learning models like ResNet50 for high-dimension vision data sets and like something like SVM and random forest for structured tabular data. And the task was to see whether the risk advisor, which is model agnostic, can sort of predict where these models would make errors, so predict the failure risks of these models. And we discovered that it surprisingly, in spite of being model agnostic, it outperforms even model aware, so the ones where you actually have access to the loss function of the model. Okay, so let me maybe move to the next point here. So now you've, often when you sort of deploy these models in practice, there are scenarios where machine learning systems often fail in unexpected ways and without giving any kind of a warning. So maybe to pick up from some of the examples in the previous sections earlier, models are often there in this human-in-the-loop kind of setup. Think about doctor and an AI system. When you have models in this space, it is crucial that models communicate their uncertainties, because these models are not always correct. As we've seen previously, they make all kinds of errors. Also, it is important to sort of consider these in a setup where the model doesn't always need to make a prediction, right? It can often decide when to abstain or defer this prediction to the fallback system or a human in that setup. So what we did was take the model that we had shown previously, this risk advisor framework, and sort of see how well can you actually use that, again, in a model agnostic way, to sort of identify when to abstain or differ from making a prediction. So these are like two of the data sets that I was mentioning earlier. where sort of the task is to, so on x-axis you see the fraction of times the model deferred to an oracle who knew exactly what the prediction should be. And on y-axis is the classification error. As you would expect, a random model, as you keep deferring to the oracle, you have this blue curve where the classification error decreases. Imagine you had an oracle which is deciding exactly when you want to give this control to an oracle, you would get this curve. That's the best possible you have. And any of the other models that you have would lie somewhere in between these two. And what was interesting is the model agnostic approach that I mentioned performed quite often at par or even outperformed the black box model's own uncertainty prediction. And this was also the case for deep neural network kind of models where uncertainty estimations are quite sophisticated as well. Okay. The other part that happens once you sort of like deploy these models in practice is over time, data drifts, right? User behavior is changing, user groups are changing over time. So the question also often comes up is, how do you respond to this changing data by updating your model, right? So what can we really do to sort of keep up with these changing data drifts? So again, the same model that I had presented earlier, we sort of recreated the scenario of simulating data drift. So on these academic data sets that I had mentioned earlier, sort of the experimental setup that we have here is for safety critical tasks like heart disease prediction. The model is only trained on hospital data from the US region, and it's applied to regions outside. Similarly, for unfairness, it's only trained on male data, and the task is to predict this for female. The question is, how do we respond? So the setup really over here is, in case of these kinds of data drifts that happen in practice, can we detect such data drifts, and can we update the model to keep up? So the main insight that we had here was that the uncertainties that I mentioned earlier, sampling based on where the model has epistemic uncertainty works sort of the best in terms of deciding where do you sample the data points. So to expand a little bit on the setup here, on x-axis is where you're sampling more data points. So as you go through, you're detecting the uncertainties of the upcoming data points, and you're adding those model to your data and updating the model there. So you're retraining them on this setup. And we observed that as few as even 10% of additional samples helped improve the accuracy by about 20 percentage point here in terms of predicting heart disease accuracy on out of distribution region. So this sort of gives you insight on how you could actually handle these kinds of changing distributions in practice. Okay, so I think with that I come to more or less the end of this talk, just to sort of summarize what we spoke about, various different challenges in terms of like how you think about fairness problems at various different steps of the pipeline, and what can we really do about them. I do want to say that this is a very growing space. There are many more open challenges to address. So I'll just talk about two of them, and each of these alone can take their own entire presentation. But I think one is about feedback loops. So we're talking about the case of fairness, and today's predictions of the model are going to be tomorrow's future data for your training, right? So any of these biases that are there today can actually get exaggerated over time as you train these models. So how do you actually identify such feedback loops and also break these feedback loops is a very open challenge, especially when you think about setups like recommendation and so on. Then the other one I think is on top of everybody's mind right now is about generative AI, right? For example, large language models that we were talking about. So how do you think about fairness in AI systems like generative AI? And this is largely an open problem. Like today we spoke about classifier setup, and here ML fairness is a very well-defined problem. You have notions of fairness, you know how to mitigate them. But when you think about large language models, it presents many unique challenges, and it's a very open space. So At my work at Google, I also drive research in the large language model space, responsible AI and safety there. So this is something that I'm happy to also chat later about, but again, a very exciting space. Okay, so I think with that, I come to the end of my talk. Thanks so much for listening. These are some of the papers that I discussed today. And with that, I open it up for questions.
Thanks, Preethi, for the interesting talk. I think we'll just take one question from the audience, if you have a burning question. Otherwise, Preethi will be here for also the mentorship session, so you can just walk in and have a chat with her. And yes, I think with that, we will end this slot, but thank you so much. That's it.